Hello viewers, thanks for checking out this video. I hope you find it useful. Today I am going to be kind of going through the process of planning out what I need to be able to heat up my garage. So I'm guessing you're already somewhat interested because you clicked on this video and you have a general idea of what it's about. But basically, I've recently moved back north and it's hit winter time, so I have an apartment garage that doesn't have any AC outlets and I need to heat it up so I can go work on my cars or go in there at any time. And I don't need it to be warm all the time just while I'm in there working. So I'm not trying to put in anything that burns fuel that would have any kind of fumes in there. I want to minimize that risk. So what I've decided to do is go ahead and heat it with a electric source. And since there isn't any, outlets or anything in that garage, I need to find a way to power it. So that is what the overall plan is for this video series. I just want to let you know in this video specifically, I'm just going to go over the logic of what I'm going to be doing and how to plan for what devices or what kind of like ratings I need to go by. So I'll make another video of me actually, putting this stuff together in the garage and doing the test and heating it, showing you guys that. But this video specifically is just going over the numbers and showing you how I came up with buying certain devices that you'll see in the next video. So if you're not interested in this, just go ahead and wait until I release the next one and I'll show you how it works out. But if you're interested in like applying these numbers to some project of your own, then I hope you find it useful. I will try to keep it simple and short. So let's just dive into it. There's really not a whole lot to this. Basically, my setup is going to be consisted of a DC deep cycle Moraine battery. I'll talk a little about that when we get to further on. Um, Next one is a power inverter to take it from that DC battery to an alternating current source so that we can plug in our device, which is the third thing, which will be a ceramic heater in this case. But this process works for just about any kind of device that you want to power up anywhere. You have an electric grill that you want to tailgate with. This is something that you could do using the battery in your truck. I don't recommend it, and I'll talk about that in a second. But um, this process is pretty much useful for any kind of mobile power source that you want to use. You can pretty much take a battery and inverter, put them together to power up pretty much anything for a limited amount of time. So in this video, we're going to go over how much time I need and how I got to that. So let's go ahead and start with the basics of how to get the rating numbers for power and current, how they're all related. So it's a pretty simple equation. I just posted up here. Power is equal to voltage times current. Um, just in case you're not familiar with it, that's how you get those ratings whenever you see a tool that says like 2000 watts. That's pretty much what it means, is that if you have 120 AC running to it and this thing um, runs off of like 15 amps, then the power rating is just going to be your voltage from that outlet in your wall times whatever the current is. So then you'll know it's an 1800 watt device, and that also works the other way around. If you see it's a power rating with wattage and you want to know what the current draw is, then you just kind of reverse this and you say, okay, it's 120, I have 1800, so divide 1800 by 120 and it'll come out to 15. So that'll be, the easy way to just remember what the actual numbers are. If they only give you one rating, you can figure out the current draw to make sure it matches your system. If you're doing like a DC system like we are, we'll only have 12 volts, and we'll be running that for, I don't know, something that has, I don't know, maybe 10 amps, and that gives us a power rating of, excuse me, 120. That's typically not as often used for DC. It's more of an AC application as far as like wattage ratings, at least in my experience. I don't really know too much about if you use DC wattage ratings. Usually you look for something like amp hours or, just the general voltage to make sure if it's 12 or 24 or 6 or, 3 like 1.5 like a AA battery. So typically wattage is stuck to 120 volt AC. So that being said, the first thing we have here is well, we'll get to this later. It's a little less common, but this first item is amp hours, and that's how a lot of batteries are rated, is based off of how long they can run a certain amperage. So if you're having a 12 volt battery that runs for um, that has a rating of 100 amp hours, that means that you have the ability to run that amount of amps for such a long time. So if you're running a 100 amp hour battery and you're pulling, I don't know, 10 amps device, then you're basically going to be able to run it for 10 hours. So you take 100 amp hours divided by the current draw and say, okay, you get 10 hours. So let me just put that into the spreadsheet here. Say you have a 100 amp hour rating battery and your device is pulling a rating of 10 amps. You just say, you take your rating and divide it by what that is, and that gives you your theoretical runtime. Now, the thing is, with most batteries, it's dependent on whether it's a deep cycle battery or just a car battery, and you, I don't know, but you shouldn't run the battery below half of it. So in actuality, if you have 10 hours of theoretical rating, your battery should only go to half of that, because otherwise it'll be kind of damaging to charge it and recharge it, because that's the whole point, is to be able to reuse this. So if you need to, you can absolutely run this to about 10 hours, but that will kind of hurt the recharge and life cycle of the battery. So if you can run it for 5 hours each time and then recharge it, then that's kind of a more ideal situation. But with amp hours, there's kind of a difference in how those are rated between regular car batteries and deep cycle batteries. So if you're doing a project like I am, where I'm just running an inverter off of this, and it's a standalone system, it's not like connected to an alternator on your car or anything, then the battery shouldn't be a car battery, because those are suited for short-term bursts to like start your car, which takes a lot of like quick current draw, and then it doesn't do a whole lot. So there's special batteries called marine or deep cycle marine batteries that are made specifically to do a longer, slower release of power. So if you do something, you can run stuff off of your car battery doing exactly this, but your battery for the car is rated to do a different type of work. It's not rated to do a long-term running work. So you would probably have to be running your vehicle while you do it. And that's not something I want to do in my garage. I don't want to be having fumes from the vehicle. So amp hours is the most common rating you'll see, but another rating you'll see on batteries, especially with the deep cycle ones only, really, is reserve capacity. And that's just kind of another rating similar to amp hours, except instead of running it at 12 amps or something, this is how long you can run in minutes a battery at 25 amps, I believe it is. So if you had a rating of like 250, that means that you are running, sorry, not 12, 25 amps for 250 minutes. So typically, in order to get from RC to amp hours, the the common general thing that I've heard a lot is just divided by two. After looking through online, a little more accurate thing that I found is to divide it by 2.4, just because there's some it's a little bit more accurate, I guess. But if you can't remember it, just remember divide by two, and that's pretty much good enough. But for example, if you have a 250 reserve capacity battery and you want to know what that is in amperes, you could say equals what that is divided by 2.4, and that'll give you 104 some odd amp hours. Is a little bit more accurate to what it actually converts to. All right, so I hope that helps kind of clear it up. So that's kind of the basics for the battery side. we'll be using a 12-volt battery in our system, and we'll be looking at one that could be RC or amp hours. I think I'm going to go with one that has an RC rating, and I'll show you like the conversion on the example, but we'll move on to the inverter. So an inverter, if you don't know what it is basically it's a device that converts voltage from DC to AC. So if you have 12 volts going in, then at the other side will be 12 volts going out. And that usually makes it so that you can plug in devices like you would to a normal outlet. That's kind of the whole idea of having an inverter, is having the ability to, like, I don't know, plug in a microwave when you don't have an outlet anywhere else. It like physically has an outlet on the inverter most of the time, or like 99% of the time. So when you run an inverter and you have nothing like connected to it just to turn it on, um, it still takes some power, so you have to keep that in mind when you have a device and the inverter running. It's not just going to be the load that's on the box rating, so it's not just going to be that 2,000 watt, I don't know, microwave that you're running to this. It's going to be 2,000 watts plus what it takes to run the inverter, which typically is only about 15 to 50 watts when you run an inverter idle. So that's pretty much the additional power that it's going to need. Um, it's really not that much. I think most of the time it's going to be lower on that scale, closer to 15 to 30, but uh, according to some stuff online, like it'll be between that range typically if you're not running anything. That's just like what it takes to run the inverter itself. So we'll just say 50 hypothetically, just for the sake of maxing out and making sure we cover all our bases. And the next item is going to be our device load, which is, like I said, it could be anything. For me, it's specifically a space heater that's going in the garage, but for you, it could be a light. It could be a grill if you're trying to tailgate. It could be anything that uses AC power. And when you go and buy a device, it always has a wattage rating on it. Every box has it, and it'll typically be something like 2,000 watts for something else. Some big space heaters are like 4,500 watts or something, but for now we'll just say devices 2,000 watt heater. So that gives us total load of both of these. So you got to remember it's a very small allowance. So not a big difference, but just make sure that what you have is rated for like this cumulative number. So inverters will have a rating on them of what they can go to. If you have a 2,000 watt inverter, maybe you'll have to step it up to like a 2,300 inverter. Oh, 2,300. There we go. So that you account for any additional pull, especially if you want to maybe plug in a secondary device sometimes, something like a small phone charger. It's always kind of nice to have that second availability in there. But if you just leave it right at that range of what the device is, then you're kind of risking being overloading this inverter. Now, this load is like a maximum load rating, so it should be kind of safe. It typically won't go all the way up to the 2,000 watts, but theoretically, let's just plan for the worst case scenario and say that is what it's always going to run at. All right, because you don't want to have a system fail a little early just because it was, really putting a big strain on the inverter. Just plan a little to give it some space. So like maybe go to a 2,500 watt inverter for something like this where you have a 2,000 watt load. All right. So next thing, this voltage, like I said earlier, since we have an inverter, our voltage is going to be 120. Your current load is basically going to be, like we said earlier, you can take your total power and convert it to what your current draw is by dividing it by 120. So we can just say divide our total load by our voltage, and that will give us the amount of current that will be running on average per hour. So, we have this amp hours. We will be running about 17 amps per hour through this battery if we run this system. So now, if we say we have a 100 amp hour battery, just to keep the number simple, and we're running it at this 17 amps per hour, then our max runtime should be that 100 divided by the 17, which means that we should be able to run this 2000 watt load. We'll say it's a grill just for fun because I just went tailgating last weekend and I wish we had something neat like this, but we used gas or propane, whatever. Um, so you could run this grill off of a battery and inverter for almost 6 hours. But like I mentioned before, you don't actually want to run it all the way down. So you only want to run the battery for about half of its life so that it has a better recharge and life cycle. So you really only want to run this divided by 2 for maybe 3 hours, which is still a really long time. I mean, that's still a very impressive lifetime for just a battery that hasn't been charged and it's just running a device. So yeah, if you run a deep cycle battery, it'll usually have a bigger amp hour rating. Most time vehicles don't have something like this. They'll have like maybe like 65 if it's a bigger one, because they're more of a large draw at a short terminal so that you can run your starter motor. So you'll really yeah, it drops off, over an hour maybe of your runtime if you use like a car battery. But at the same time, if you want to and you're at a tailgate, you can always start your truck and then actually be running the grill while the truck is running so that you can actually keep the battery charged. But in my project, we will not have anything running. So now that's kind of like the theoretics of it. I guess down here I put this into just sometimes you'll see a device actually has a current draw rating on it. So if you have one that says like it draws 20 amps and it's obviously a 120 volt system, then you'll know that your inverter rating should be enough to handle that load if you're shopping for the inverter. So you know that your inverter needs to be able to handle a wattage of 2400 at least. And again, the inverter itself takes about 50 or so. So you might want to look into at least a 2500 watt inverter if you're running something that draws 20 amps. So if you don't have like wattage ratings, if it's a device that gives you current, you're trying to figure out what kind of inverter load you need. It's pretty simple to figure out from doing just that. All right. So now for my system specifically, I am hoping to, be able to get a deep cycle battery. We'll clear this out. That will pretty much heat up my garage for, maybe 2 to 3 hours at a time. I'll be out there for maybe let it sit for half an hour before I go there to kind of warm up a bit, and then sit there for maybe 3 hours at a time. Hopefully, get enough done on the vehicle to make it worth sitting out there. And I think that's a pretty good goal. And I can bring it up to my apartment and recharge it, go out the next weekend or whenever I have time during the week. And that seems like a good goal for me. So we want to shoot for an actual run time of like, maybe 2.5 hours. But we'll, the nice thing is, if you set up these numbers, you could just start with 100 and say, like we did, 50, device load 2000. That'll give us the sum. We'll put these equations back into place just so that, whoa, oh, sorry, that was not supposed to be multiply, that was supposed to be plus. So then, if you're not sure what kind of device or runtime you're actually getting, you can define devices online, put them into here to say, oh, I found a grill that's actually 3000, and that'll update your total load for you. So I recommend just making a little quick spreadsheet like this. And for your current load, again, you're going to take total wattage divided by your AC voltage now because it's been converted. And then you take your max runtime will be the theoretical amp hours divided by your theoretical load. And last but not least, put in our actual runtime that we see. Oh, not times, divided by 2. So, if theoretically now I couldn't find a 100 amp hour battery, I only found one that's 90 amp hours. So now I know I need a little over 3,000, little over 3,000 watt inverter, and a battery will last me about an hour and a half. And again, you could also double check if you don't know what inverter you're getting. You just put that current draw is 25. Well, let's say keep it in the formula here. It's the whole point of Excel. And it is 120 equals that times voltage, because power equals voltage times current. It's like the whole project really just boils down to this equation, guys. I mean, that's really all it is. So yeah, get an inverter that's ready for something like this. But I did a little shopping, and I did find a a Stanley ceramic heater that does a 1500 watt load, and it's Stanley. I found another video of somebody rating it, and they said like it's not that powerful, but it's enough to like be comfortable, and that's all I need really, is something that I can blow the heat somewhat in my direction. It doesn't have to heat up everything, just at least in the area that I'm at, and I can still wear a sweater and stuff while I'm there. But when it gets to like 10 degrees out, I really just don't want to sit in the garage burled up wearing gloves. So now that we have our device load, we have our total. Next, so that gives us our total load current of almost 13 amps. So we need an inverter of at least 1550. And I did plan on getting one that's around 2000, just because I may want to add a work light to this. But I have battery powered one, so that's not a big concern. And I looked at where I can go shop for deep cycle marine batteries, and I did find one that actually has a RC rating of what was it? I believe it was like 230. So my amp hour rating for it is divided by 2.4, because it's, if you don't remember that, divided by about half. And now with this 95 amp hour ish rating, this should last me for about 3.5 hours, which is a little bit more than I really wanted. But again, if I'm going to be running another device on it to bring it up to like 1800, say I got a 300 watt light bulb, it's not very big, but it's something that I'll be able to just plug in. Then it'll run it for 3 hours ish. After some time, the battery will have a little less life to it. So this is like theoretical runtime. But for now, my plan is to get this 1500 watt heater, and I am going to look for an inverter that's rated for at least 1600, probably go up higher to a little, around 2000 or so, just so I can have that extra device. And this 230, so remember that 230 means that it runs 25 amps for that's however many minutes it runs 25 amps. So if you want to see then hours, you just put that into divided by 60. So this thing runs almost 4 hours of 25 amps, which is, almost doubling what we're running. And this is a very small heater. So most devices will be like, if you want an actual garage space heater, they're closer to like 4,000. So on an actual size one, I'd only get like an hour and a half out of this, but that would like really toast up the place and make it incredibly warm and comfortable. And I'm not that choosy. So this is what I'm looking for. I'll go through cost really quick lastly, just because I already know I've been rambling on. I apologize for that. But the battery of this caliber, or something about 100-hour amp hour rating, um, those are about, I don't know, maybe 150 to 200 bucks on average. Um, so just in case you aren't sure what kind of budget you're looking at, if you're looking here, we'll put it amp hour in case you guys need to screenshot this. We'll say 2000 watt inverter. I believe typically those will run somewhere close to the same range as the battery. If you're running a smaller setup, then you can get a really cheap inverter for like 50 bucks. That'll work just fine. I think Harbor Freight even sells them, so you can maybe find one on sale. But for an actual inverter, there's a pure sine wave and not a pure sine wave. That's more like a square. So it'll come up and over this. Yeah, I can't draw it with Excel, sorry, but basically a pure sine is a little bit smoother, so it's okay to use with other devices that are needing more consistent power. If you have like a non-pure sine wave, that's kind of a cheaper inverter. It's more sketchy powered and a little ticky-tackier. Like I'm just switching my mouse around. But a smooth, pure sine wave one is actually going to run devices better and not damage them. So it's, to me, it's worth paying the extra money. I mean, 2000 watt one will probably be, I don't know, like 180 bucks, close to 200. So similar to same range. And then the ceramic heaters are actually going to be the cheapest part of this system. Ceramic heaters are much cheaper than just regular electric heaters. So I definitely recommend looking at those. You can get those stand-up ones that are like 40 bucks. And I think those are like 3000 watt heaters. And they're like maybe 50, 60 bucks for those. So overall, I'm looking at maybe a total of $460 to be able to heat my garage or power any other device. So I'm still gonna try to find like an electric grill, and I can just run this at our next tailgate and not have to be buying propane all the time. Um, it may work out, it may not. I can also use the inverter in my car. Maybe I'll set up something so that I can have an AC plug-in for a short time later on. So once you buy these items, just remember, like, it's especially with these two combined, you're not just paying it for a garage heater, you're paying it for pretty much power anywhere. So if your power gets shut out and like there's a thunderstorm, you can just put these together and have power for maybe 2 hours if you have it charged. And that's just, maybe that'll save you. Maybe you'll run the heater to like keep your house warm during the storm. So just remember that when you guys are looking at this investment, is it's not just this one big lump sum cost. It is a little expensive to get the battery, but I think it's worth it in the long run. It'll last me like 5 years. So that's pretty much it. I hope you guys found this useful. Again, I'm sorry if I rambled on a little bit long, but please put in your comments or thumbs up, thumbs down, any suggestions of what I can do to make these kind of things better. But the next video for this I'll put out is me actually with the parts that I bought, putting it together in the garage, and I'll show you guys like, before and after of the system working, maybe do like a runtime test. So be on the lookout for that if you're interested in seeing how well this actually worked out. Thanks, and I'll see you next time.